Hello everyone, my name is Timur Yusupov and I will be presenting in this presentation. I would like to introduce the topic that I have chosen is the convolutional neural networks, and particularly I will present one application which is a video classification with convolutional neural networks. First of all, I'm going to talk about the definition of convolutional neural networks, and then I'm going to talk about other methods which are used for classifying videos. And I'm going to talk about actual using of CNN for video classifications. What are the CNNs? The convolutional neural networks have been extensively used in image recognition tasks. Particularly, they were used in object detection, image summarization, retrieval, and segmentation. Later on, I will talk, as I mentioned before, I will talk about the other methods and the video classification with CNN. The most important requirement of convolutional neural networks is achieving high rates of accuracy, however, enormous datasets of images with labels, and methods for scaling up the models to millions of parameters. So, as we learned from the lecture, fully connected neural networks is about finding a global pattern in an image. They find global patterns in image because they are fully connected. So each layer of each neuron of one layer is connected to each neuron of the next layer. Because of that slight clarification, to decrease the accuracy, and it decreases the accuracy, and that's why it's a very big problem. So in a real scenario, for example, digits, they're different, slightly different, because of the connectedness, and there are too many parameters for a large enough image. Convolutional networks, they try to solve some of those problems by introducing promotional filters. Convolutional filters, which instead of looking for global image, they look for local patterns, and you can see that in the image how it's described. So the convolutional filter part, the dissemination pixel, and the source of pixel. So those people, they try to train themselves, so the user doesn't have to define the filter. Also, they are for competition, for reducing the competition costs. The most crucial neural network is one of the most first crucial neural networks is LeNet5, and you can see it here. It's one of the most crucial neural networks. So sets of conclusion in subsetting are followed by 4 connected networks. So there are also many different advancements. For example, AlexNet, which introduced by convolutional layer and dropout for avoiding overfitting, and new activation function 55 limit units. It has a wider convolutional layers, require layer unit, and dropout. Dropout is about removing some neurons to some iterations randomly. Standard neural net, and it's after applying the dropout. So it removes neurons randomly to some iterations. Other improvements include the deeper networks, larger filters, replaced by several smaller filters, and bottleneck, which is further reduce overfitting. And there are some approaches for modification. One of them using first the consists of 3 steps. So first of all, this is a classical approach. First of all, it's local visual features are extracted, and then those features are turned into the spectral histogram, and the histogram used on a classifier, and the classifier would try to classify based on the given categories. It's also classified as a bag of words, the second name. So these are the recurrent neural networks. This is another approach which uses recurrent neural networks. So because the videos are temporal and have temporal significance, recurrent networks are actually better than CNNs, and they use different kinds of neurons, as we can see it here, neurons to control and preserve memory from previous states. And for example, in case of video, they preserve the information from previous frames. And earnings, if they use optical flow, the performance gets better, and if they use the optical flow, the optical performance will get better. Is about recording the movement often of a video in time. As we can see there here through the lengths, the green dots provide the optical flow. So as an image, the first paper which I read it's tried to use different types of architecture to be able to train the videos. So it had a large data set of videos. So to do that, they use different kinds of architectures to compare with each other. So one of them was single frame, and in this case you can see that red layers, convolutional filters, and green layers are pulling layers, and blue layers are food layers. Normalization layers are yellow and fully connected layers. So this is a very simple single frame. Is a very simple type of architecture. It records one frame at a time and doesn't record the temporal significance of videos. The next one is a light fusion. And yes, so light fusion, early fusion, solar fusions, they're all record, slow fusions, they all record the motional videos using multiple frames. While single frame only records motion, not proportional awareness, so it doesn't record the motion. As we can see here, the differences to single frame networks, as it has a global motion, it has a pixel region, local motion direction, and local motion speed. Slow fusion is a connectivity, higher layers, more global information, and since it has a higher layers, and it gives more information, and then temporal spatial convolutions. So this paper also used the new technique called Fourier and context streams. So it's instead of using the original video, they use 2 streams of half the size of the original video. And one stream is about getting the center region of a video of the original size, and the second stream is about getting the whole video but half the resolution. So using this approach, the cost can be reduced more than a half. So they use this kind of settings for optimization and preprocessing. They preprocess particularly using random flipping with 50% probability. So here we can see the downpour statistic. Here's how they calculate the probability, and this was a training data set. It was so here. This is a processing, copying, random sampling, random flipping, as I mentioned before, with a 50% of probability, subtracting the mean of pixels, and 100 seconds. The dimension is 170 to 170. So this was a training data set. It was about 10 a.m. So it was on topic of sports 1M. It was 487 classes, and 1 million YouTube videos. And these are predictions based the predictions which were achieved. So as you can see, the slow fusion got the best. Slow fusion got the best results. So the video heat is about getting the best, the correct result. And video heat 5 is about getting at least a correct prediction. First of the most frequently predicted, as we can see here, video heat 1 and heat 5. So slow fusion was the best, but the difference with signal frame was little. So as you can see it here, it's not that big difference, 42.4 and 41.9. Very small differences. And even though the accuracy was not that great, you can see that the misclassification is more reasonable. Because, for example, in this case, cycling was chosen, but the correct one was track cycling. And obviously, track cycling are very similar. And yes, here we can also see the different comparisons, the difference between the slow fusion and single frame. So you hear the performances of the differences. The model was trained to transfer learning dataset, and it's called Düsseldorf USCF 101, and it contains over 13,000 videos and 101 of category. And it's not only sports, but all other different topics. The model was strengthened by using the same parameters and early layers, but on top of 3 layers. The model was fine-tuned and it achieved the best results. And it all fitted terribly when trained from scratch. So we can conclude that earlier parameters could be generalized for other datasets. Here we can see other categories of videos also got pretty good performance. Next, I will discuss another paper which uses other architecture, which is LXNet and GoogleNet architecture. They used a different kind of approach. They used future pooling, which is used in classical approaches of video classification. In this case, future pooling refers to running static convolutional layers on all frames of the video, which are labeled as seen red, and then they applied pooling layer to summarize the features of all those frames, and this way the author tried to temporal significance of sub-videos. So they use different kind of approaches of doing this, and they pair with each other. We will see the results later. So as overall it says, they apply pooling layer to summarize the features of all of those frames, and this way the author try to temporal significance of sub-videos. And as we can see here, convolutional pooling achieved the best results. It hit in all 3 hits 68.7, 71. It got the highest. The convolutional pooling is different from other types because it performs future pooling directly after convolutional layers, and because of that, the temporal significance served as much as possible. In comparison, others didn't save temporal significance as much. Because of that, the accuracy was better as after analysis. GoogleNet overall, most of them overall performed. GoogleNet performed better than AlexNet, as you can see here. When using the optical flow for convolutional pooling, the difference was not as big because the quality of selected videos was not in higher performance for the datasets they were taken from YouTube. But when the model was applied to another dataset, it got better results when using optical flow, when we used the dataset UFC 101. So in conclusions, we can say that CNN architecture far surpasses feature-based methods